Yeah, so yeah, this is the outline of the talk. So I'll spend the first, like, I don't know, 18 or 20 slides to introduce a bit the concepts that I will use later on, and then I will move to the results. As Sergey said, I'll mostly concentrate on two-dimensional system. Most of them are halides, halide system with transition, 3D transition method. Okay, so yeah, very quick introduction. Let me see if I can. Okay, do you see the mouse? Do you see my mouse moving?
Yes, I do.
Yeah, okay. Yeah, so basically I work until, October. I had worked in a central part of Italy. So Rome is on the Tyrrhenian side. We are on the Adriatic side, so eastern part. And I lead a small group. So here you see especially Paolo Barone and Danila Moroso, who are the main contributor to the results I will show today. Oh, sorry. Okay. And then I moved to Milan recently, to the University of Milano Bicocca. So in my career, I worked mostly on oxides and also on hybrid material with some organic and inorganic blend. And then I moved to the magnet, and I'm a theorist. So most of the results I will show are derived within density functional theory, but we benefit a lot with collaboration with people doing symmetry analysis or also model Hamiltonian. So Flatland. So Flatland, as probably you all know, they are material which are, 1 atom thick or few atom thick system, and these layers are held by van der Waals, by weak bonds, weak forces. And they are interesting because they offer a lot of functionality, some of them being different from their 3D counterpart. So the biggest advantage is that you can, stack very easily 2D magnets one on top of each other, much, in a simpler way than with 3D counterpart, without having to bother about, interdiffusion or lattice matching. So in this sense, they are more flexible than 3D material. Also, there are new areas that are emerging, like this twistronics, so the fact that you can, twist the two layer and get, different pattern, which also result in different functionality. Also, you can slide, this layer, and there are effects such as ferroelectricity arising just because you slide two material one on top of the other. This is like sliding ferroelectricity. Also, they are easily bent, so you can get some curvature effects, for example, magnetic effects being induced by the curvature and the radius of the curve. And so these, of course, are typical of 2D material. I mean, you can do this with 3D or with thin film, but let's say it's more complex. So they are flexible in this sense. So, of course, everything started with graphene, but then as for our, interest, the birth of 2D magnets actually happened in, I don't know, 2016 or 2017, where people could actually prove that there is a long-range magnetic ordering in prototype material, which are typically chromium iodide or chromium germanium telluride, or also this iron phosphorus sulfur. And so unambiguously, there was an evidence that the material order at the 2D level. So these 2D magnets, I find them pretty interesting and pretty various. So, for example, from the chemical point of view, you can change the anion, putting a chalcogen or halogen. You can find binaries or ternaries, and also from the crystallographic point of view, you can find triangular lattices and honeycomb and rectangular, so they're, again, pretty various. From the electric point of view, they are semiconducting or insulating, and of course they are rich for magnetic properties. So you can find some that are ferromagnet, some are antiferromagnet, and then, as you will see in the talk, some even exhibit complex spin texture, like non-collinear and maybe non-coplanar. And also as for the anisotropy, you can find them having magnetization out of plane or in plane. So the class of material is itself pretty interesting and various. Okay, so there are many challenges. Most of them have, especially the insulating ones, most of them have Curie temperature which are typically low. By low, I mean like 50 or 60 Kelvin, so they are not room temperature. There are some metallic ones that might be more promising in this respect, but on average, the ordering temperature is pretty low. Especially the halides and the iodines in particular, they're very sensitive to humidity, and so they are not that stable in air, and it's also pretty different to scale them up. So you can find flakes, you can exfoliate flakes, but not to a large range and not with a large control. These are more like, I don't know, technological challenges, but I'm a theorist, so I'm mostly concentrated on the challenges that are present in this class of material as for microscopic understanding and modeling. One word which we cannot avoid to say in a talk on 2D magnetism is that, of course, if you have Heisenberg spins or isotropic spins in dimension lower than 3, then long range order is in principle impossible. And this is where some source on anisotropy, and we'll mostly concentrate on spin-orbit coupling, comes into play. And so if you have anisotropy, this Mermin-Wagner theorem doesn't hold anymore. So the microscopic ingredient in which we'll spend some time during the talk is spin-orbit coupling. So let me say a couple of words about this interaction, which is the coupling between spin and angular momentum. And for most of the materials we study, like 3D based system, this is like a small interaction compared to other energy scales at play. It's much smaller than hybridization, but still it gives rise to interesting physics. And so in solids, both in non-magnetic solids and in magnetic solids, it gives rise to a lot of interesting physics. So many of the topological non-trivial effects that have been studied during the last couple of decades are in many cases rooted within spin-orbit coupling. So as some exotic band structure effects like Rashba or Dresselhaus or spin valley coupling, in many cases they are driven by spin orbit. And of course in magnetic solid, that is very important. The easy axis or easy plane is actually driven by, in most cases, by spin-orbit coupling. And there are also some exotic exchange interaction that are microscopically driven by spin-orbit coupling that we will also see during the talk, such as Chelosy-Skimoria and Kitaev-like. So most of the talk will be on transition metal halide. So let me spend a word on it. So this here I show nickel chloride or bromide or iodide, but then I will also discuss about vanadate, and these are very similar from the crystallographic point of view. So you can form a 3D layered van der Waals crystal with this material. The nickel form a triangular lattice. They are octahedrally coordinated. There is a slight trigonal distortion, but not that large. So trigonal, and so the Z direction, the the direction perpendicular to the layer is actually perpendicular to one of the faces in the octahedron. So okay, nickel here is the 8 with a high spin configuration means that we have 2 Bohr magneton on each nickel. And then I'll focus on the trend for chlorine, bromide, and iodide. So as I move down to in the periodic table, of course, I expect spin orbit, atomic spin orbit coupling to be larger. And so yeah, I expect that with iodine, all the spin orbit effects are stronger than in their fluorine counterpart. Okay, so this material were actually studied already in the bulk forms in the 80s, for example, and already at that time by neutron diffraction, I believe, they were found to show some complexity. But of course, at that time, nobody thought about exfoliation, and so this is actually what we concentrated on. And so checking the properties of nickel halide, not at the bulk level, but at the monolayer level, or bilayer, but mostly monolayer. But already in the bulk, some complex magnetism was found. Okay, so one more ingredient about frustration, which I will discuss more in the part of the talk. Okay, so the paradigm of exchange frustration is that if I have a triangle with antiferromagnetic exchange interaction, then if I try to place 2 spin on a triangle with an antiferromagnetic interaction, then the third spin wouldn't know what to do. If it lines up, then this bond is frustrated. If it lines down, this bond is frustrated. And so the system somehow tries to find a compromise by achieving this so-called 120 AFM spin configuration. So it tries to minimize the exchange interaction that are at play. And this exchange frustration is strongly connected to the kind of lattices that the material has. And so you find exchange frustration in Kagome lattices, in 3D, in pyrochlore, but also in triangular lattices, which is what characterizes the material that we are interested in. So we, at least from the crystallographic point of view, we have the ingredient that we need to have exchange frustration. Even if you have a spin chain, you can have frustration. For example, if you have like one weak exchange, it can be ferro or antiferro, but it should be small at the first nearest neighbor level. But if you have like a second nearest neighbor exchange, which is strong and antiferro, then 2 things can happen. If you have a strong anisotropy, so you have like easing spins, then the ground state would be like an up, down spin chain, so that at least the second nearest neighbor is always satisfied because it's antiferromagnetic. If you have Heisenberg spins and the anisotropy is not that strong, then the ground state is like a spin spiral. So the spin rotates from side to side. If you have sufficient condition, like strong second nearest neighbor, which is antiferromagnetic. Okay, the other ingredient I wanted to introduce is that okay, typically, of course, the first model that comes to our mind is the Heisenberg, when we model when we do a spin model, is the Heisenberg coupling, in which we have a scalar term which couples 2 spins. But then in principle, this is not the whole story. We can describe the coupling between 2 spin by a 3x3 matrix. And I can always decompose from the linear algebra point of view a matrix in like a trace term, which is isotropic, in an antisymmetric term, and in a traceless symmetric term. And so from the physical point of view, this isotropic one is the Heisenberg term. This antisymmetric is generally called Cheloshinsky-Moria interaction. And then there is this other term, which is usually neglected. So it's presumably small, much smaller than the other two, which is an anisotropic exchange. And so these three terms, what do they do? So the Heisenberg, of course, depending on the sign, tries to couple the spin with a parallel or anti-parallel arrangement. But it's isotropic, so it's the same if the spin are like this, or like this, or like this. The Zielinski-Moria interaction, it's a cross product, so it's zero for parallel spin, and it therefore tends to count the spins, and so it's generally referred to as a chiral interaction, and depending on the sign of the D vector, the counting will be like clockwise or counterclockwise. This anisotropic exchange does what? It also tends to align to spin along a certain direction, much in the same way that the single ion anisotropy would do. But this is a pairwise term, so it gives a preferred direction, but it arises from the interaction of two spins. Okay, and already, back in the, I don't know, 60s, Moria showed that they are rooted in the spin-orbit coupling. So you expect this material to, this interaction to be strong if you have like heavy elements. Okay, so from the symmetry point of view, there are Moria rules, which give some, prescription on the direction of the D vector and on the existence of the D vector in some, any kind of space group and crystal with certain symmetries. So in our case, we have inversion symmetry, crystallographic inversion symmetry in our material, which forbids Zielinski-Moria. So when we try to calculate this J tensor, we will have only symmetric terms, and in particular there will be also some zeros in the matrix that dictated by the space group that characterizes the nickel halide. So there are in total 4 independent terms, 3 on the diagonal and then 1 symmetric term. Occasionally during the talk you will see also non-coplanar structure, and so I wanted to spend 1 slide on the magnetic skyrmion. So what are these? So these skyrmion are actually topologically non-trivial nanometric magnetic spin texture that were discovered in many material. And then there's a zoo of skyrmion, and there's a zoo also of anti-skyrmion. So the difference between skyrmion and anti-skyrmion is that in an anti-skyrmion, the winding, let's say, of spins change if you change direction. They can wind, for example, clockwise in one direction and counterclockwise in the other direction. And these are typically 2D spin texture, but then you can think about their topological charge by wrapping this 2D sheet of spins around a sphere. And so they are characterized by a topological charge. And so there are different descriptions, but in our case, we had a triangular lattice and with spin localized on sides. And so the way we define the topological charge is the sum of some contribution coming from each of the triangle, where we have a triple scalar product defined like this. So a scalar product of 1 spin times the cross product of 2 other on the triangle. So already from here you see that to have this topological charge to be non-zero, then you not only need non-collinearity but also non-coplanarity. And yeah, phase diagram of many systems showing Skyrmion is actually complex and common. So most of them have some, helical. They start from something which is already a bit frustrated, so like a helical spin system or spiral or conical. And then if you apply a magnetic field, then you get into a region in which you have Skyrmion. Okay, because I will also discuss multiferroicity, let me just introduce what ferroelectricity is, which is redundant, but let me just spend one slide on it. So ferroelectric material is a material that shows the presence of permanent and switchable dipole below a certain temperature. So you have much in the same way as ferromagnet, you have a critical temperature below which you have an hysteresis cycle, not in the MH space, but in the PE space. And you have the emergence of the order parameter of the transition, which is polarization in this case, below a certain Curie temperature. And they not only need to be polar, but they also need to be switchable. So you need a plus p state and then a minus p state, which are isoenergetic. And so ferroelectrics material are typically used when you need bi-stability. So you can build, for example, non-volatile memory element out of ferroelectrics. So typically ferroelectricity arises because you have an inversion symmetry breaking driven by the movement of ions. So the center of mass of the positive charge doesn't coincide with the center of mass of the negative charges. But you can also get ferroelectricity by spin configuration. So actually there was a boom back in the beginning of 2000 when they discovered that actually if you have a spin spiral, so spins that rotate from side to side, then you can find an emergence of ferroelectric polarization. And the way you switch the direction of P is actually by going from a clockwise spin spiral to a counterclockwise spin spiral. And this was very clearly shown in manganite, like terbium manganite, where it was clear that there was the emergence of ferroelectric polarization below the Néel ordering temperature. So this unambiguously showed that there's a strong link between ferroelectricity and magnetism. Okay, so again, this is kind of particular class of ferroelectric in which you have ferroelectricity induced by electronic degrees of freedom. And they are different from conventional ferroelectrics because, as I said, it's the ion, it's not the ion that give rise to ferroelectricity, but it's a kind of electronic order that emerges, which breaks inversion symmetry, and as a byproduct, you get ferroelectric polarization. So this is why it's called improper. So in a proper material, you only have one order parameter, right, of ferroelectricity, for example. But here, ferroelectricity is like a secondary order parameter. The primary order parameter is something else, like a magnetic order parameter, or also if you have like charge order, if you have like orbital order, they can also drive ferroelectricity. Okay, so I think I'm done with this, first part. So I wanted to know if there are, questions, or I'm very, happy to answer at this stage before I move to the,
Right. So if there are any urgent questions, so please. All right. So that's fine. That's fine. So let's go on. I have one, but I will ask after the talk.
Okay. Good. Yeah, so then I will ask question. So the question I wanted to ask is whether, we can have 2D magnets that show exotic spin texture. This is not, obvious, right? That because, the field is new and was new when we started. So first thing we wanted to check is whether we can have, non-collinear or non-coplanar spin texture. And so we focused on this nickel I2, which is, as I said, characterized by triangular lattice. And in first approximation, we extracted by mapping total energies calculated by density functional theory to a simple Heisenberg Hamiltonian for the moment. We got basically a strong ferromagnetic interaction at the first nearest neighbor. Second nearest neighbor was basically 0. And third nearest neighbor was found to be strong and anti-ferromagnetic. So if I now remember my picture about the spin chain, if I move, for example, along one direction, one of the 6 equivalent directions here in the lattice, and I try to place my spins so that they satisfy this J1 and J3, then, okay, I know that my J1 is ferromagnetic, so I try to place this spin up, but I also know that the third nearest neighbor is strong and anti-ferromagnetic. So you see that there is a frustration, right? Along each of the spin chain, the spins cannot, satisfy all the interactions that are at play. And so because of this, and because of the simple model that I showed in the beginning, we expected some non-collinearity, right? Already by the exchange frustration that we calculated in nickel I2. So we expected like a spiral. Okay, then we went on and we calculated the full tensor, not just the Heisenberg-like, but we calculated all the elements that are present. And so we did it for nickel chloride, and in nickel chloride, we basically got a pure Heisenberg picture. And despite, allowing for possible additional effects, what we could actually calculate is that you have 3 diagonal elements, no off-diagonal elements, and the 3 diagonal are the same. For nickel bromide, you start having something that deviates from Heisenberg-like. And for nickel I2, we actually got quite strong off-diagonal terms. These are all calculated with spin-orbit coupling. Otherwise, of course, you don't get any of this, deviation from Heisenberg-like. And because if I compare nickel chloride, bromide, and iodine, what changes is not the nickel, but what changes is the anion. All the effects that we are seeing must actually come from the anion. So it's a sock of the ligand, it's spin-orbit coupling of the ligand that gives rise to this effect. Okay, so but with DFT, you can only do, small system and 0 temperature. And so to have some hint on the temperature dependence of the material, we generally use Monte Carlo simulation. So we use our parameter calculated by DFT to a spin Hamiltonian, which in this case contain like a tensor pairwise interaction in a tensor form, and then single ion anisotropy. Okay, just a word about the notation. So you have, of course, here we are allowing 3-dimensional spins, which are represented by arrows, but the way I will show is by showing black arrows which are projection on the 2-dimensional plane, and then by color I will show the Z component. So if they point outside of the paper or board or inside. Okay, so what we did was that we did first perform Monte Carlo simulation for nickel bromide. And so what we got was this. So the susceptibility shows that you have low Curie temperature. It might, this depends a bit on the parameter that we use, whether you use U or not U, but it's certainly like small, like 20 or 30 Kelvin. And what we see here is that we have a helix. So you have a propagation direction like horizontal, and then the spins rotate in a plane which is perpendicular to the propagation vector. And this we expect. So it's like a cycle, it's like a helix, so it's like a spin spiral, which we expected because we know that we have J3, and which is antiferromagnetic, and J1, which is ferromagnetic. What we didn't expect was actually what we obtained for nickel I2. So for nickel I2, we obtained something like this. So we recognize a periodic lattice, but at that time also we were not very experienced about skyrmion and anti-skyrmion, but we thought it could be, something like this. And so we tried to evaluate the topological charge of this, and so discovered that these are anti-skyrmion with higher order, not Q equal 1, but Q equal 2. And so you can take basically a topological charge as a order parameter. And so again, the Curie temperature, order in temperature here, it's pretty small, like again 20, 30 Kelvin. And so when we discovered, it was the first example of skyrmion in 2D magnets, and these are a bit unconventional with respect to 3D counterparts, because usually skyrmion are driven by Cerussy-Schimoria interaction, right, which is a chiral and gives rise to non-collinearity and maybe non-coplanarity. But here there's no DM, right, because it's forbidden by symmetry. So it had to be something different. And also, this is obtained without magnetic field, whereas in many cases you have a skyrmion when you apply a magnetic field. So this is like a ground state. What I said, it's correct up to a certain point. So it's a ground state. What I mean is the following. So it's a ground state, but then basically at the same energy we have a spiral. So we have a helix. The helix and the anti-skyrmion are basically very close in energy, they're closer than what we can say, basically. The difference in energy is below our numerical accuracy. So I would say that it can be, one of the other, and actually in the remaining part of the talk, when we compare with experimental data, it's very likely that actually nickel I2 has a spiral and not an anti-skyrmion. But at least the mechanism, so I'm not sure that, let's say, nickel I2 is the material that would show anti-skyrmion, but on the other hand, I'm also pretty confident in the fact that if you have a strong exchange frustration with a large anisotropic exchange, then you can in principle achieve this like 3Q anti-skyrmion state. Okay, so first answer to the first question is that, we can have exotic spin texture. And so the second question was whether, some of these exotic spin texture could actually induce ferroelectricity, much in the same way as it was, studied in the oxides. And so with this, we actually got in touch with the professor at MIT, Riccardo Comin. And so he in his group, they exfoliated nickel I2, and then they characterize with via some collaboration by optical means, and also by nonlinear effects, nonlinear optical effects, so like second harmonic generation and optical birefringence. And they were studying the signal obtained in one monolayer, bilayer, 3-layer, 4-layer, and bulk. And so what they observed was that there's a signal which is not zero, and the signal, the temperature at which this signal emerges decreases if you go from bulk to one layer, but still, even at the monolayer level, you get some signal. So it orders somehow, even at the monolayer level. The other additional information that they gave us was that through second harmonic generation, one can do a symmetry analysis. And then they could tell us that the threefold axis that you have it because of the crystalline operation was actually broken and reduced to a twofold symmetry. This is why we thought that it could not be a skyrmion, which would still be characterized by a hexagonal symmetry, but it was in pretty much a helix. Okay, but still, even though we were not happy our anti-skyrmion was not found, still we thought that this spin helix could give rise to some nice physics, because a spin helix can in principle induce ferroelectricity. And so actually, again, back in the 2000 or 2003 or six maybe, there was five. There was a model proposed by Katsura Nagaosa-Balaski, in which they basically explain through spin current the emergence of ferroelectric polarization as driven by the cross product of two spin, cross product with the vector connected to spin or propagation vector. So in most of the multiferroics, you have P that is perpendicular to the propagation vector, to Q. And so by this simple model, you expect that if you have a spin helix, so you have like a S cross S, which is parallel to the propagation vector, you shouldn't get any polarization. However, again, this is a model and in principle could not hold for all the materials. And so one can calculate by density functional theory a generalization of the K and B, in which I basically try to couple the polarization given by two non-collinear spin by the cross product of two spin by a three-dimension 3x3 something I call a magnetoelectric tensor. Okay, and we can evaluate all this term in this tensor by, again, DFT, and then by summing up the pair contribution, I can get my macroscopic polarization in my whatever spin texture I have. Okay, and so the K and B would be a specific case of this general 3x3 form, in which I would only have one independent element. And so we did that for nickel I2, and actually the situation was pretty different from a simple K and B model. And so if you then sum the contribution coming from all your spin in skyrmion or helix or whatever spin texture you find, one can have polarization. And so in the helix case, we could get the emergence of ferroelectric polarization below, again, the magnetic ordering temperature, which was consistent with what Riccardo Comín found. And so this is why we proposed this nickel I2 to be the first improper multiferroic in the 2D world. Okay, so answer to the second question is also that, yeah, you can have 2D multiferroics. Then we wanted to expand a bit the class of material. Also, yeah, I told you that there was a lot of, emphasis on the multiferroics in the first 2 decades or first decade of year 2000. But then it was mostly oxide. So the role of the anion was never investigated just because, anion was fixed, was always oxygen. Here we have the possibility to study the effect of the anion on ferroelectricity. Okay, and so to do this, we moved to a slightly different class of material, but the cousin of the nickel halide, the vanadium halide. So here I have vanadium D3, which fills half of the T2G shell, and the EG is completely empty. Okay, so if you calculate vanadium, the exchange constant in vanadium halide. This has a first nearest neighbor, which is anti-ferromagnetic. So we expect this to be a realization of the 120 Nel state that I showed you in the beginning. What we couldn't say pretty much from first principle was whether this 120-degree state had spin lying in the plane or spin lying out of plane. They were very close in energy. So we are not sure whether this is the ground state or that is the ground state. So we did both of them. And so again, we tried to estimate the polarization arising from this kind of non-collinear spin texture. Okay, I forgot to say an important thing is that when you have polarization driven by a generalization of Katsura-Nagaosa-Balaski model, the polarization that arises emerges from spin-orbit coupling. And so we expected that nickel I2 or vanadium I2 in this case would have a larger polarization than vanadium chloride, which is not the case. So of course, if you kill spin-orbit coupling, everything goes to zero. So that spin-orbit coupling plays a role, it's sure, but also that something else probably matters is also probably true. Again, you can change, okay, this was also known by the oxide, right? But if you change the plane in which the spin rotate from, let's say, if they rotate in plane or if they rotate out of plane, you can change the direction of polarization, which also happens here. And also, okay, before claiming that these are ferroelectric, one needs to calculate the double well profile. And so here, because again, these are improper ferroelectrics. So the double well is not achieved by restoring centrosymmetry in the ionic position and making the opposite displacement, but it's achieved by changing the spin configuration. So we went from a, let's say, clockwise spiral to a counterclockwise spiral through a paramagnetic state, paraelectric state, which in this case, it's like a ferromagnetic state. So if you do the calculation by forcing the direction of spin and progressively moving from clockwise to counterclockwise, then your total energy would, start from a minimum, go up in energy, and then go down to the second minimum. So this is like a proof of the double well in spin space. Again, you can apply an electric field in reality, but also in DFT, because we have like a single layer perpendicular to the layer. And then you should be able to stabilize, let's say, the clockwise spiral versus the counterclockwise spiral that are isoenergetic if you don't have any electric field, because plus P and minus P are degenerate. But if you apply an electric field, then you should be able to stabilize one or the other. And this is what we actually see. Okay. Yeah, so I told you that there is more than simple spin-orbit coupling. And so we thought that maybe structural effects could play a role. And so, okay, the optimization of this material is a nightmare. So we wanted in the beginning, I think we tried to see, for example, if we change so if we optimize the structure with different amount of spin-orbit coupling, what changes in the ferroelectric polarization. But these are tiny effects, so it didn't converge. And so to examine the structural effects, we did something very brute. So we did the following. So we have like 3 lattice constants, one which characterizes vanadium chloride, second one which characterizes vanadium bromide, and third which characterizes vanadium iodide. And then we fixed the structure and we just did the chemical substitution in each of the 3 lattice constant. So for vanadium chloride, we actually put vanadium bromide and vanadium iodide, and for the 3 lattice configuration, just to see if I change the structure, what would my polarization look like? How it would be affected? So try to disentangle, let's say, the chemical effect by having, larger spin-orbit coupling, large atomic spin-orbit coupling in iodine and chloride, compared with the structural effect. So having the ions, closer and different hybridization channels. And the effect that actually arises from changing the lattice constant is pretty strong. So for example, if you just look at the orange one, for example, if you look at the vanadium bromide when the atoms are close or when the atoms are far, the polarization is sensibly affected. So the total polarization is not just the result of atomic spin-orbit coupling, but it really depends on the details of the hybridization and how the atoms, the electronic levels, actually, electronic orbitals interact. Okay, so in addition to the nickel halide, we have the vanadium halide, which also might be, interesting to study. So the last couple of minutes, I wanted to say, okay, so far we looked at spontaneous effects, so multiferroicity, so spontaneous emergence of ferroelectricity and magnetism. But in principle, we might also induce, ferroelectricity because we apply a magnetic field, so more related to magnetoelectricity, so some non-spontaneous effect, but coupling between ferroelectricity and magnetism by applying external fields. And so to do this, we chose another class of material, which is manganese phosphide with a chalcogen atom. We took sulfur and selenium. And so these are not triangular, but have a honeycomb structure. And so from the experimental point of view, they are known to be anti-ferromagnetic. But also in our case, because manganese is D5, the difference in total energy between having the spin in plane or out of plane was not that easy for us. So again, we consider both spin configuration. Oops. And so we did the following. So for example, if my spin are in the plane, so they are anti-ferromagnetic, but lie in the plane. And if I try to apply a magnetic field like this, which I can't really do in calculation, but I can say I mimic the effect of a magnetic field by counting the spins. And so we counted the spin, we basically followed, counted by, I don't know, 5 degree, 10 degree, 15 degrees, and so on and so forth, the spins, so as to mimic the action of a magnetic field in plane, and then estimate the if polarization emerged. And we did this configuration, so we spin, let's say, in horizontal direction and H in the plane, or we apply H out of plane. So if you apply H out of plane, then you expect your spin to count out of the 2D sheet. Or you can also do this if the spins start by having this configuration, so the spin are perpendicular to the two-dimensional plane. You can still apply a magnetic field in a horizontal direction, which would count their aligned antiferromagnetic. So if you apply a magnetic field, they would count in this direction. And so in all these cases, we basically calculated polarization as a function of the spin counting angle. And this is what we observe. So, okay, of course, the effects are small, right? You have like microcoulomb per meter square. So all these, spin orbit induced effect that cannot be compared to polarization that you have in barium titanate, which is order of magnitude larger. but still you can have some effect. And also you can switch, of course, this polarization by inverting the direction of the magnetic field. So in this way, basically, we proposed a class of material in which you don't have multiferroicity, but you can have some improper magnetoelectricity. And so, yeah, this brings me to my conclusion. So I told you that you can, play Lego and stack all this material in the way you want. And so there was, graphene in the beginning, and then a ferromagnetic Lego brick and a ferroelectric Lego brick were also discovered. And then now we also have a multiferroic brick that we can play with. Okay, and with this, I would like to thank you for your attention.